nematic superconductors.
Okay, thank you very much. So first of all, I'd like to thank the organizers for the invitation to this excellent meeting. And so first of all, I'd like to explain the project we are doing, which is called quantum liquid crystals. So the reason why I'm here is that our project, the quantum liquid crystals, is one of these 10 international network on this quantum materials accelerator. And I was very happy to have a postdoc fellow award to Wei Yao. So we are actually very happy to hosting him in the University of Tokyo, and he will come just after this meeting. So I will give a brief introduction on what we are doing on this quantum liquid crystals project. Yes. So as you know, there is a huge field on this quantum fluid or quantum liquid in electronic systems. And I think Joe had a very nice introduction that there is a kind of analogy to the classical fluid. And if you look at the classical systems, you can make a symmetry breaking to introduce the liquid crystals, and there is a huge field of the so-called soft matter physics. And if you go back to this quantum fluid or quantum liquid field, there are several novel concepts emerging, including superconductivity and quantum Hurry. So our idea is to introduce symmetry breaking in this quantum liquid systems to have a sort of kind of analogy to liquid crystals, to have so-called quantum liquid crystals. So one example of this kind of QLC states in electronic system is this this strongly correlated metallic systems. So here is the atomic image taken by SPM by Taka-san. And if you look at the atomic images, you can find a four-fold symmetry of the tetragonal ensemble. But if you look at the electronic states, there is a kind of one-dimensional object that has a similarity to a liquid crystal. So you can call this like electronic liquid crystal states with broken rotational symmetry. Then this example is on this correlated metals. So then we can find another kind of new states of matter like electric nematic phase or charge stripes. But if you go to, let's say, an insulator, and you can take a look at quantum speed systems, you can also have similar kind of novel states like spin nematics or chiral spin liquids. And even in superconducting state, you can find the FFLO or pair density wave states that have a broken symmetry. So our idea is to define these electronic liquid crystals-like state and kind of try to unify these concepts as quantum liquid crystals, QLCs. So our kind of project is try to find the universality and diversity of these QLCs and try to elucidate and control these QLCs. So that's our kind of project. And we have actually currently 52 researchers in Japanese Institute. And if you want to have some international collaborations, you can just take a look at the our website, which is hidden here, but it's qlc.jp. Okay, so let me focus on one of our kind of achievement in this QLC projects. And today I'd like to discuss the iron selenium-based superconductors, which seem to have a very exotic superconducting state. Okay, so this work has been done in collaboration with these people listed here, and the main players are Kohei Matsura and Yuta Mizukami in our group in the University of Tokyo, in collaboration with Tomo Uemura in Columbia University and Tetsuo Hanaguri in Riken. Okay, so let me start with the general kind of classification of the superconducting gap structure. So I think you know very well that you can have a fully gap state, and you have kind of point nodes or line nodes in the superconducting gap. And for example, if you have this kind of nodal superconducting states, and if you apply a magnetic field, what happens is that you can actually have vortices, and around this you have a supercurrent going like this. Then you can induce the low energy states, which is called the Borovic. Okay, so this kind of things have been around and well known. But recently, there is another kind of theoretical proposal that we may have another new class of superconducting states having two-dimensional nodes, which is called as Bogoliubov-Fermi surface. And in such a case, you can have a finite zero energy state even in the absence of magnetic field. And then, but this kind of very exotic superconducting states, you need a very strong requirement that time reversal symmetry must be broken in the superconducting state. So this kind of idea has been developed by Daniel Akterberg and others. And they start with the Bogoliubov-Dujan Hamiltonian and to make an anti-symmetric matrix, H tilde. And then they can actually mathematically define the so-called Papian, P of K. Okay? So the meaning of the Papian is that Papian equals 0 gives you the zero energy states for the Fermi surface. And in the normal state, for example, the Papian looks like this. And the Papian 0 gives you this kind of Fermi surface in the usual sense. And if you go to the superconducting state below Tc, usually this Papian becomes positive. Then your Fermi surface is fully gapped. So that's the usual case, right? But in unconventional superconductors, you have nodes, it's like a point nodes or line nodes, in which you have a Papian 0. However, if the time reversal symmetry is broken in the superconducting state, you may have a condition that Papian becomes negative at certain case. And in this particular example, you have this kind of torus. And inside the torus, the Papian can be negative. And then this Bogoliubov-Fermi surface is kind of topologically protected by this negative Papian. And on this torus, the Papian is 0. Okay? So that's the kind of the theoretical proposal for this Bogoliubov-Fermi surface. So you may say that this is kind of, yes, please.
A very ignorant question.
Yes.
So when you say the superconductivity with broken time reversal symmetry,
Right.
so then what happens with so-called time reversal domains?
Right. So you
They
can,
show as a
it can be
fluctuation
chiral.
or domain?
Yeah, it can be chiral. So for example, the time reversal symmetry breaking is saying that your order parameter is becoming like A plus IB kind of state. So you have, then you can have a chiral domain corresponding to A plus IB and A minus IB. So this is the domain.
So
So,
You should have a static domain.
well, yeah,
Fluctuation.
yes, I think
Static.
it's static.
I see. So, but if you do real experiment without magnetic field, then you're going to average out basically all these domains.
Right, you can control by the magnetic field.
You can control.
Sure,
But,
sure.
Thank you.
Right. So this kind of thing can be understood by saying that it is a kind of spontaneous Borovic that can be, that have a finite residual density of states, even in the absence of magnetic field. which is related to the broken time reversal symmetry. Okay. Then in 2020, the group of Peter Hirschfeld have shown some models that maybe iron selenium-based superconductors can have this kind of Bogoliubov film surface in certain parameter range. And here you can find the normal state film surface, which is shown by red. And in superconducting states, you can have this kind of Bogoliubov film surface in the zero temperature with different parameters. And if this is the case, you can have a zero energy quasi-particle density of states in the ground state, in the superconducting state. So that can be tested by, for example, specific heat, which you have residual C over T. And you can also see the tunneling zero energy conductance like this. Okay, so that can be tested experimentally.
So as you go, sorry.
So what's the difference between these quasi-particles and Majorana fermions?
Okay, so it's not Majorana. It is just quasi-particle density of states at zero energy.
No, I understand, but so
It is a completely anti-symmetric Hamiltonian,
Right.
and as such, it is really a Majorana Hamiltonian.
It is Majorana fermions, but it's not Majorana zero modes.
it's
Yeah.
not
It's a
Majorana
difference.
zero modes. I know that. It's just Majorana fermions. I was just thinking these should be Majorana fermions.
If this is the case, it's very interesting.
Yeah, because okay, we can talk later.
Okay, so let's look at the experiment. So I'm an experimentalist, so I'm not a theorist. So we are kind of studying this iron selenium-based superconductors, which is very interesting. And it has a so-called nematic transition at 90 Kelvin, below which you have electron anisotropy within the plane. And what is interesting here is that we have no magnetic ordering down to zero temperature, meaning that this electron nematicity is a pure nematic phase without magnetism. Okay? And from the quasi-particle interference measurements, the superconducting gap have been shown to have a very strong anisotropy. It has a deep minima, or maybe it has a nose in the superconducting gap. Then this electronematic transition temperature 90 Kelvin can be suppressed by using this isovalent substitution. You can substitute selenium with the isovalent sulfur. And you can actually completely suppress the electronematic transition. And you can find evidence for the nematic quantum criticality by the measurements of nematic susceptibility, which can be measured by using the elastoresistance technique. Okay? And what is important here is that we can do quite high quality single crystals by using the CBT technique. And you can actually take a look at the STM topographic images in which you can find the position of sulfur atoms. And this sulfur is uniformly distributed. And you can even find very clear quantum oscillations in a wide range of sulfur compositions, meaning that we have a pretty clean system. So this is actually very important to study the intrinsic physics in these materials. And this nematic quantum criticality can also seen in the transport measurements. And we can have this very linear temperature dependence of the resistivity down to a very low temperature if you apply a strong magnetic field to suppress superconductivity. And one can find the very unusual temperature dependence of the whole. Okay, so but here today I would like to focus on the superconducting state. So we can measure the series of the specific heat down to very low temperatures by using the so-called long relaxation calorimetry technique, which can measure the very specific heat in a very high precision for the very small crystals. And from this kind of data, we can construct a thermodynamic phase diagram like this. So this is temperature, this is sulfur, and here is the nematic transition temperature, and this is Tc, actually 2 times Tc. Okay, and first of all, the Tc shows a kind of jump from like 9 Kelvin to 4 Kelvin. So we can say that we have 2 different superconducting states. We call SC1 inside the nematic phase and SC2 outside the nematic phase. And if you look at the temperature dependence of electronic specific heat, C over T, you know, the temperature dependence is quite different between SC1 and SC2. And in SC1, it shows a pretty normal structure. You have a jump, and you have a kind of temperature dependence goes to 0. Right? However, in the SC2 region, we have a very, large superconducting fluctuations above Tc, and more importantly, we have a very large residual density of states like this. Okay. Now we can also take a look at the STM spectra, which have been done by Hanaguri-san, and here is the sulfur conditions, and here is a nematic critical point. And inside the nematic phase, we have a kind of V-shaped spectra, which is consistent with a very strong anisotropy in the superconducting gap. However, if you go to the SC2 phase, then you can find a very large zero energy, zero bias conductance. So if you define this zero bias conductance divided by the gap edge, then you can find that it shows a jump from a very small value to a very large value if you go across the nematic quantum factor. So it's clearly that this SC2 region, we have a very large zero energy states. Okay? So this seems to be quite consistent with what Peter Hirschfeld have suggested theoretically. And but one important ingredient to have this kind of Bogoliubov phase surface is that the time reversal symmetry must be broken inside the superconducting state. Yes?
Are you suggesting also that it's a triplet?
Well, so from the experiment, for example, if you look at the HC2 curve, it shows flattening behavior at low temperatures. So I cannot say it's triplet. There is no clear evidence for triplet.
Okay, so are you going to talk about what's breaking time reversal symmetry?
A little bit, but yeah. So
That's
then
okay.
Yes.
Can I ask a question? I'm just trying to connect this to the iron selenium tellurium system. So in this high sulfur regime,
Sure.
is it the same
Right.
phase as the iron selenium tellurium?
So I don't have time to talk about this today, but if you do tellurium, you can also suppress the
Yeah.
nematic transition,
Yeah.
but TC is actually enhanced.
Enhanced.
So it's kind of different, and we don't see any evidence of it.
I know the properties are different, but if they're both tetragonal phase and no nematic
But
phase,
in
so
terms of the
it's nominally
nematicity,
the same.
it's similar. Okay, so the next question I would like to address is that whether the time reversal symmetry is broken or not in this material. So we have performed the zero field USR measurements, and which is a very sensitive probe of the internal magnetic field inside the sample, and so which can be used as a direct probe of the time reversal symmetry method. So we have measured the 3 samples. One is iron selenium inside the nematic phase, and these 2 are outside the nematic phase. Okay? In all cases, we see that the USR relaxation rate is enhanced below Tc, which is an indication that we have some kind of magnetic field appearing inside the sample below Tc. So this is evidence for the broken time reversal symmetry in these samples, both in SG1 and SG2. Okay?
How much field does that represent at the
Okay.
U1 site?
It's like less than 1 lux. So it's a very small magnetic field here,
How much less than one?
like 0.3 or something. Okay, so here is the kind of experimental summary. So first, the phase diagram shows a kind of jump in TC, and then zero bias conductance from STM, which is plotted by this brown symbols, and also residual density of states plotted by pink from spectroscopy. All of these shows the jump if you go into the SC2 phase, okay? And then there is another experiments which have been done, which is the transverse field μSR, from which we can measure the superfluid density, which is 1 over a penetration depth square. Which is related to the ratio between the superconducting electron carrier density divided by effective mass. And this is plotted by these red dots, which can be compared to the normal state n over m star, and in which n represents the total carrier density. Okay, and this can be estimated from the quantum oscillations measurements, which is plotted by this blue line. And as you can see, if you go into the SC2 phase, you can see big deviations. So this means that very large number of electrons remains normal, which is consistent with the presence of some kind of Fermi surface left inside the superconducting state. Yes.
So in the nematic case also, you have only 2 points, right?
Right. So yeah, it's a time consuming measurement, and so we have actually 2 different x, and here we have a quantitative agreement between these 2, and there is some deviation, but it's not that big here. But here you see the very big difference. Okay, and the recent calculation by Peter Hirschfeld group shows that they can actually estimate the diamagnetic current response or superfluid density as a function of some kind of parameter, and they find the stable Bogoliubov frame surface in this hatched area, in which you can find the that the superfluid density should be strongly suppressed from the original value. So this seems to be kind of consistent with what we have observed in μSR results. So from these results, we conclude that we have evidence for so-called ultranodal pair state with Bogoliubov frame surface in iron selenium sulfur in SC2 phase. Okay, so then I asked the laser archives people. This is the data taken by Okazaki-san in ISSP, and we provided samples in the SC2 region. And they found that in the normal state, they can find a C4 symmetric firm surface, which is consistent with the tetrahedral crystal structure. But if you go into the superconducting state, if you look at this 90-degree firm surface around here, they see a clear opening of the superconducting gap. However, if you look at 0 degree, which is around here, they don't see the opening of the superconducting gap. So they can analyze the gap size as a function of firm surface angle along this line, and find that they find some extended angle range in which the superconducting gap does not open. So that's actually consistent with the presence of the Bogoliubov frame surface in this iron selenium sulfur. But we were surprised to see this result, because that in the normal state it has a C4 symmetry. However, the superconducting gap structure has a strong two-fold symmetry, right? So for some reason, there is some rotational symmetry breaking occurring just below TC. But we can say that it is kind of consistent with the presence of the nematic Bogoliubov frame surfaces, or you can say that it's two-dimensional nodes with two-fold symmetry. So we have no kind of solid conclusion about why we have this kind of rotational symmetry breaking. But recently, there are two theoretical proposals for the nematic bubble surfaces, and we need more experiments to verify which kind of scenario is more useful. Okay, this is the final slide, and I would like to also say that from the NMR measurements, we can also see very strange things happening here. And for this 18%, which is in the SC2 region, 1 over T1T in superconducting state at low temperatures, you see enhancement of the 1 over T1T, which is an indication that we have some kind of spin fluctuations inside the superconducting state. So that may be due to the kind of nesting properties within the bubble frame surface in the superconducting state. Okay, so let me kind of summarize my talk, saying that we have evidence for time reversal symmetry breaking throughout SC1 and SC2, but we have only, evidence for bubble frame surface for SC2 region. So there is some kind of topological transition to go from SC1 to SC2, and SC1 is, you can say that it's a nematic time reversal symmetry breaking superconducting state, and SC2 is the multimodal superconducting state with the frame surface. But here is an open question. Why does the suppression of nematicity drive the topological transition to this bubble frame surface state? That remains open. So, we have very, exotic and very strange results experimentally, and there are a lot of work we need to do still to understand this very exotic superconductor. So let me put the summary slide here, and thank you very much.
We have time for maybe two questions. Yeah.
Sorry, just to clarify, I mean, I just had jumped into the conclusion that it was triplet or something like that, but if it were, then of course you would have Majorana fermions. Your Bogoliubov quasi-particles would be Majorana fermions. But if you have just broken time reversal symmetry for some other reason, I don't know, Pierce, then what would you say? What are these
If I'm not mistaken, I thought these ordinodal superconductors were basically triplet superconductors, aren't they? To make this, you've got to get rid of the spin degree of freedom at the Fermi surface. It's not those gapless Fermi surfaces and do not have a chromatodegeneracy in them. They're just spinless.
If that's true, then these are Majorana fermions.
So I think this is a triplet superconductor in the proposals, no? It must be triplet, right? It's not a singlet superconductor. It's not a D plus ID type superconductor. It has spin structure to it. But I'm surprised, maybe the word triplet is a dirty word in ion-based superconductors, so people are scared to say it.
Well, so you say that the reason why we have this very large zero energy states is some part of the spin component.
Well, I think if you look at the Achterberg original theory, it's triplet superconductor to start with. So I think these Bogoliubov Fermi surfaces are all triplet superconductors. So if you're seeing this here, this is a triplet superconductor, which is very, very interesting.
Right.
Because it flies completely in the face of accepted wisdom for the ion-based superconductors.
Okay, so but we don't have any evidence for, for other evidence for triplet.
But I think having a Bogoliubov Fermi surface is game, set, and match to begin with.
Well, there's got to be experimental signatures though, right?
Yeah, okay.
More experimental signatures.
Yeah.
No, but you don't know what those quasi-particles are, though.
No. But if it were a Bogoliubov Fermi surface, then I think it would be a triplet superconductor.
That would be very interesting, but we need to...
Or maybe there is other mechanism to get that, because that might be just one reasoning, the octagroup sort of mechanism, right? Maybe there are other mechanisms to get that.
I think if it's an anti-symmetric matrix, right? An anti-symmetric matrix always splits up into Majorana component. So, I don't know, I have to look at it more carefully. We have, I must say that similar Fermi surfaces appear in various odd frequency superconducting scenarios, and these are triplet, and they do have Majorana fermions in them.
Okay, so I can say that in this SG1 phase,
Mhm.
at least, people believe that it's kind of a spin singlet state.
Mm.
So if this is this transition is, like singlet to triplet, that is another interesting scenario. But we don't have any kind of experimental evidence judging whether this is either spin singlet or triplet.
It's
So
very
we need
difficult to tell if you've got an entangled triplet state, whether it's triplet or
Very
singlet.
interesting, yeah.
Very difficult to tell.
So one last,
Very quick question. When you say that topological transition, you really mean in terms of Pfaffian, change of sign of the Pfaffian changes? What do you mean by topological transition?
Yeah, so, if you give this scenario, Pfaffian negative, before the surface, you must have a Pfaffian negative region. But here, you don't have it.
well, thank you again. We have one more talk, but that will be after a break. So there's a break, and all the students who are, and all those who are presenting posters, they should make sure that posters are in place. We'll come back for one more talk after the coffee break, and then. Thank you.
The moment you see a Pfaffian, you know it's Majorana fermions. A Pfaffian is a classic evidence of a.
Like, for example, system right now.
That's a good question.
There are other ways to break down.
So you only have the Fermi surface on one side. With the sulfur, the high sulfur doping is only on the side. I had a question. Did you consider using pressure? Because sulfur is smaller than selenium, so it must be like positive pressure.
And is this a laser? But there is it's dual. So
I had to do fun, so that's why.
so thing
Then it's gonna,
All right, so, welcome back, everyone. So our final speaker today is Alana Hallis from UBC and CFAR. And she's going to tell us about understanding the role of entropy in high entropy oxides.
Thank you so much. So it's a pleasure to be here, and I know that as the final speaker of the day, I have a tough task ahead in terms of keeping you all awake. I do promise if you stick with me that my talk will very literally end with a bang, so stay tuned for that. Okay, so I'm going to be talking about a very different class of materials from what we've been hearing about today, and these are materials that are known colloquially as high entropy materials, and I'm specifically interested in high entropy oxides. And just to set the stage for what I'm about to tell you, it helps to think about how high entropy oxides might relate to other classes of materials where we use engineering as kind of a way to alter the material's properties. And so I think a fantastic example of this comes from the field of heterostructures, where we know that if we grow two dissimilar materials on top of one another, the properties that emerge at the interface can be distinct from either of the adjoining materials. And so this is a great way that we can engineer electronic properties. A more recent example is the field of twistronics, where we know that if we stack now a similar material at some non-natural stacking angle, we can again modify the electronic properties of the materials just by altering that stacking motif. And so I like to think of high entropy materials as very much existing within this paradigm, where instead of using this stacking kind of engineering, I'm instead using a chemical engineering to tune the properties of the materials. And so what we have here is a crystalline material. So my atoms are located on a well-defined crystal lattice, but you can see that I've color-coded them with 5 different colors representing 5 different chemical elements, and they're all sharing a single crystal lattice. And what we're hoping to see here is some property that emerges as the result of this chemical disorder that's not present in any of the kind of native oxides that make up the material. Okay, so this is kind of our canonical picture for a high entropy oxide. It's actually a rock salt structure where the oxygen atoms are confined to a completely ordered sublattice, and it's only the cation sublattice that is disordered. And I would argue that it's quite a beautiful picture, but it's not entirely clear that such a thing should be real or that it should exist. And so what we can do to sort of validate the existence of such a material is to look at a number of different probes along many different length scales and also in both real and reciprocal space. So one of our requirements for high entropy oxides is that they should be crystalline, meaning that on average, they obey translational symmetry, that we can describe their structures with the language of space groups, and that if we do a diffraction experiment, we should be able to measure sharp resolution limited peaks, and that's indeed what is found. We can also look at a very local length scale with a technique known as atom probe tomography, where the material is fabricated into a tip, and atoms are evaporated off the end of that tip, and we can reconstruct through a time of flight mass spectrometry a 3-dimensional image of where the atoms in that material were located. And so what we see when we do atom probe tomography on a high entropy oxide, you might be able to see these very faint speckles, which are all overlapping each other on this leftmost image. The point that I want you to sort of gather from this is that the positions of those atoms, which are marked by the colored pixels, they're not separated or clustered. They seem to be, at least to a first approximation, randomly distributed throughout the material. So we have these 2 requirements: random chemically, but crystalline on average. And this picture that I've presented to you is reinforced at every length scale. So we can look with different electron microscopy techniques, as well as pair distribution function. In every case, we see a picture that is consistent with what I've just told you. So those 2 requirements alone are not entirely sufficient for defining a high entropy oxide, because one class of materials that does already fulfill the definition I've given you is just a conventional solid solution, any material where I take 2 elements and mix them on a lattice. And so to deserve this kind of special name of high entropy materials, we would like there to be an additional criteria that distinguishes them from conventional solid solutions. And the criteria that has kind of emerged as, I would say, the most prominent or the most recognizable is to quantify the configurational entropy that the material exhibits. And so we can calculate the configurational entropy, which represents the number of different ways I could arrange my different elements onto that lattice. How many possible configurations can they have? So in the case where I have just one element, a normal crystalline material, my configurational entropy is 0, because every configuration of those elements is identical to every other configuration. And in a high entropy material, the number of possible configurations is of course going to grow with the number of elements involved. And so we can write down this formula, which is just related to a Boltzmann entropy formula, which says that if we sum up over I, which is the number of chemical species that we have in the material, and we look at the fraction, x subscript I, of that species on a specific lattice site, if that value exceeds 1.61 R, we define the material as being high entropy. And that is not an arbitrary number. That number actually happens at the limit where we cross over 5 components in the material. So whenever we have 5 elements in equal proportion, equiatomic, we say that the material crosses over from a medium entropy to a high entropy threshold. Okay. Yes, of course.
So that formula doesn't have only have the number of atoms, right? Only have number of elements, but doesn't have any like crystal structure or how they arrange. So
Yeah, that's right. Yeah, so it doesn't presume anything about the symmetry of the lattice that the atom inhabits, and that the elements inhabit. But that's going to be a core theme of what I'm going to show you today.
Thank you.
Any other questions?
Yes, is there any reason why you would declare something medium versus high?
Well,
Where do we put this boundary?
why do we put this there? Yeah, that's actually just what I'm about to tell you.
Oh, okay.
Yeah, so it is empirical, to be very honest with you. But there's a couple explanations I can offer. One is that if we look at a typical Gibbs free energy equation and you have an enthalpy of formation and an entropy term, if we want the entropy term to dominate over the enthalpy term, the kind of typical energy scale where that happens is around when we cross from 4 to 5 elements. That's when entropy can begin at kind of typical synthesis temperatures to be larger than the enthalpic term, meaning that entropy in that case can actually choose the crystal structure that the material forms in instead of enthalpy. So that's one energetic argument for why 5 is special, but that's just on average true. Another kind of set of explanations comes from different functional property measurements. So this is an example of high entropy materials that have been fabricated into a lithium-ion battery. And we're looking at the specific capacity, so how much charge that battery can store as a function of cycle number. And so the legend here is a little bit covered, but the gray, red, and yellow cathode materials all have 4 components. And it's only the turquoise one here that has 5 components. And we see that its stability as a function of cycle number is very robust, whereas the other 3 all fail in relatively short order, meaning that somehow this material is better able to withstand this kind of violent lithination and delithination process. So there does seem to be some entropy stabilization effect, and that's kind of a common theme in the field. Another example is from the field of thermoelectrics, where we can look at, again, the thermal conductivity this time as a function of temperature. I notice that this is on a log scale, where I'm plotting compounds with increasing configurational entropy up to this one that actually has 6 components. And what we see is that there's a systematic suppression of the thermal conductivity, which is useful if you're trying to maximize your thermoelectric figure of merit, which is ZT. And one thing to point out here that's actually quite remarkable is that these materials are crystalline, but this lowest thermal conductivity material has a thermal conductivity that is actually lower than the amorphous limit. So there are quite remarkable properties that are found within these entropy materials, which brings me to my question. My kind of interest in these materials and the question that got me excited to study them is entropy really what's important here? And what is its actual role in dictating these observed properties, and how can we control it and understand its influence on these materials? So before I go on, I would like to introduce you to the team of people who've carried out much of this work. I'd also like to maybe highlight, since this is an ICAM meeting, that we've been awarded a number of ICAM travel awards for my postdocs Mohammed and Solvay to travel to the lab of Hide Takagi and perform high pressure synthesis experiments on these high entropy materials. And so that's been a really wonderful way to kind of launch this collaboration with Takagi's group. So the outline for my talk is going to involve 3 kind of interrelated stories. I'm going to start with the tunable magnetic order of these materials and our approach to entropy engineering. And that work has been led by my PhD student Mario Gonzalez Rivas, and my master's student, Graham Johnstone. And we've been lucky to collaborate with Robert Green, who's does a lot of his research at the Canadian Light Source. Okay, so my representative high entropy material that I'm going to be speaking about today is a spinel high entropy oxide. And it's made up of the 5 elements that go across the transition metal block in the 3D row. So everything from chromium up to nickel. And again, they're in equal proportion, so an equal ratio of those 5 elements. And if we mix them together under appropriate conditions, we can indeed form a single phase material, as we can see from this X-ray diffraction pattern. And it has the cubic spinel structure. But immediately, what we can appreciate as different about the spinel structure versus the rock salt example I showed you earlier is that I no longer have a single cation sublattice. I now have both a tetrahedral and an octahedral sublattice in the material. So my yellow ions here sit at a 4-fold coordinate oxygen environment, and my blue cations sit at a 6-fold coordinate environment. A second feature that kind of excited us about this structure in the context of high entropy is that in addition to the many elements that can sit on a spinel structure, we also have 2 nominal cation valences, 2+ and 3+. And they are, although they are normally, that is the actual technical term in the field, in a normal spinel, the 2+ sits on the tetrahedral and the 3+ sits on the octahedral, they can in many cases invert. And we saw that immediately as a source of additional entropy, potentially. Third, and this was actually the main design criteria, we wanted an entirely magnetic high entropy oxide. So at the point where we made this material, there were no completely magnetic high entropy materials. And we were eager to study how the disorder of a high entropy material would interplay with its magnetic state. And if we wanted to make a 100% magnetic material, there was really no better place to look than this particular part of the 3D block. You would have to really make a special effort in an insulating oxide to make any of these 3D transition metals non-magnetic. Yes, Sam?
Well, in some sense, you have actually 10 different elements,
That's right.
right?
In fact, 11. I'll show you. Yeah. Yeah, great. And you know, a thing that has recently occurred to me is that, first, there's entropy when we think about isotopes as well. And yeah, entropy is everywhere. Yeah.
No, I have a question. Maybe you'll get to this, but with the spinels, they're often susceptible to distortions. So you have these super structures like the 3,4,13 or the I don't know, multi-unit cell structures. Do you see any of that?
Yeah, no, we don't see any structural distortions down to 2 Kelvin, but I'll show you shortly. There's local distortions galore.
Right, and the ones that I'm mentioning, you don't see distortions of the unit cell per se, but the coordination polyhedra are tilted such that the unit cell may stay the same, but the symmetry differs.
Yeah, so these materials at a local length scale are different everywhere. Every coordination polyhedra is different from every single other one. Yeah. Yes.
Yeah, I'm too dumb. So what's the 10?
Oh, so I think what Song is saying is that you have 5 elements and they can have 2+ or 3+ oxidation states. And so nominally, yeah. Although a couple of those we can straightforwardly kind of disregard. You have to work pretty hard to make nickel 3+, so we're not likely to see that. Yeah. And then because we wanted to study the interplay of disorder and magnetism, it was useful to have a tuning parameter for playing with that magnetism. And we've used the tuning parameter of dilution, where we are systematically replacing our magnetic cations with gallium 3+. And we've studied compositions of 0, 10, 20, and 40% gallium. So we're going to be able to percolate or dilute the magnetic order. Okay, so I'd like to begin with my kind of characterization of the 0% gallium sample. So this is our completely 100% spinel high entropy oxide. And what we found when we measured the susceptibility of this material, actually the first thing that we found was that we didn't understand what we were measuring because we were measuring from room temperature to 0 Kelvin. And as someone who has exclusively studied magnetically frustrated quantum materials up to this point in my career, I didn't contemplate the possibility that a material could order, say, above room temperature. And so it turned out that in some dusty corner of our lab, we actually had this thing called a furnace that could go on the MPMS and that we could measure the susceptibility to much higher temperature. And so once we had done that, we could see this beautiful onset of long-range magnetic order, which is marked by bifurcation in the field-cooled and zero-field-cooled susceptibilities. And so right away, we were thinking, oh, we have something like ferro or ferrimagnetic order. And we didn't have to wait much longer to get a little bit more insight than that, because from magnetization measurements, we can see that our low temperature magnetization is saturating at just shy of 1.5 Bohr magnetons normalized per formula unit. But we know that a spinel unit cell has, or sorry, a spinel formula unit has 3 transition metals. AB2O4 is the conventional formula. So that means that my 3 transition metals together are producing a saturated moment of only 1.4 Bohr magnetons. That's very small for 3D transition metal local moments. The moments that we would expect to see for many of these elements would exceed 5 Bohr magnetons. And so there's no way that a long-range ordered state involving all of those elements could produce a saturated moment this small, meaning that there has to be some moment cancellation. So this limits us to looking at ferrimagnetic order. There's some partial sublattice cancellation at the moment. Yeah.
Sorry, what's the compound of this one, or this particular?
Oh, okay. So this is this material here. So it's a chromium, manganese, iron, cobalt, nickel in equal proportion.
Oh, okay.
Yeah.
Okay.
So 0% gallium. So I'm always going to refer to them by the percentage galliums.
I have 2 questions. So the mixture of the 5 transition metals is more or less 1 to 1 to 1?
Yep.
Is there any glass in this?
So I'll come back to that in a bit, if that's okay. Yeah.
There's T-star.
Yeah, so.
No, but the glassiness would be,
T-star.
no, it would be where the bifurcation happens.
Well, that's what happens. The split.
Mhm.
No, the T-star is much lower. The bifurcation happens at 350, right?
Well, okay. Too much sleeping.
Yeah.
How do you synthesize the symmetry?
Great question. So this sample is made by solid-state synthesis, but the second part of my talk is about the synthesis method dependence, where we make this material by 5 different methods. So stay tuned. Okay, so we have a ferrimagnet. Just to make sure that our assessment was correct, we performed powder neutron diffraction. And so this is how we know that there's no average structural distortion down to 2 Kelvin. So it's a bit difficult to see, but this is a measurement that was collected at 500 Kelvin, and this is a 4 Kelvin measurement. And so you can see there's been this massive enhancement of that 111 Bragg peak, meaning that a magnetic Bragg peak has formed on top of that structural Bragg peak. So we know that the magnetic order has the same unit cell as the crystallographic order. And then we can perform a symmetry analysis to actually refine the sublattice moments involved. And we get out what we expected, which is a ferrimagnetic arrangement where my tetrahedral moments and octahedral moments are anti-parallel to one another. And what was very satisfying is that the saturated moment that we see from magnetization is in beautiful agreement with the calculated moment from the neutron diffraction. Okay, so now we can look at what happens as a function of gallium substitution, where now we're going to systematically replace, again, in equal proportion. So my 5 transition metals are always going to stay in equal ratio, and I'm just adding in more and more gallium, 10, 20, and 40%. And so if we look at the susceptibility as a function of temperature, we can see that there's a systematic suppression of the onset of magnetic order. It's only 4 compositions, but it is nice to know that when you actually plot this on a graph, TC versus gallium, it is exactly linear. So I don't know if that extends all the way down to 0. And then when we look at magnetization, we can see something a little bit less trivial is taking place. So again, our 0% reference compound is 0% gallium here in blue. And when we begin to add in our non-magnetic ions, the first thing that happens is that the saturated moment actually goes up. So we have a larger saturated moment for these 10 and 20% gallium samples. And it's only when we've replaced nearly half of all of the atoms in our structure with something that's non-magnetic that we actually see a suppression of the saturated moment. And then the second thing you might observe is that the coercivity dramatically increases as we go from 20 to 40%. We see an order of magnitude increase in the hardness of the magnetic order. I won't have time in my talk today. We do know the kind of microscopic mechanism that's leading to this. And if you're interested, please ask me later. And I think
What is the motivation to change just the gallium percentage?
so. Gallium is non-magnetic, so it's the only one that isn't contributing to the magnetism. So we're basically studying how the magnetism is diluted systematically.
And sorry, remind me that the gallium is equal parts with the other three chemicals?
No, it's so it's closest to equal parts at the 10% level. Yeah, but the other 5 are always in equal parts. So if I have 20% gallium,
Oh, I
the
see.
80% that's left over divided by 5. Yeah, exactly. So just to maybe answer a little bit more thoroughly, one of the things that we were hoping to be able to compare with is conventional percolation theory. So it's very well known from sort of network theories, both just in pure mathematics and also in real materials, how much of a network you have to take out before the collective behavior will disappear. And so our thinking was that a high entropy material might behave very differently because of the disorder. Unfortunately, we actually can't get in enough gallium to get all the way to the percolation threshold, so we don't actually know the answer to that question. Okay, and then just briefly, we've also performed neutron diffraction on the gallium substituted compounds, and the main thing to point out is that this change of behavior here is not explained by a change of the magnetic structure. The material is still ferrimagnetic with the tetrahedral and octahedral sublattices opposing one another.
Have you gone to higher fields?
No, we have not. Well, these, we've gone up to 7 Tesla.
Are you seeing all the moments, or are you just seeing the net moment?
We're seeing the net moment, yeah.
That's what I meant, so you want to try and see all moments.
But is it possible that your gallium substitutes preferentially on some of the sublattice that's not being cancelled, and that's why the moment is larger or what?
Yeah, so this is exactly what we're coming to, which is, you know, we don't know anything actually. The neutrons can only tell us about the average moment on each site. It tells us nothing about the individual moment on any given site, and we know nothing about how our 5 transition metals have preferentially occupied these 2 sublattices. Okay, so this brings me to my new favorite technique, which is X-ray absorption spectroscopy, which we've been performing at the Canadian Light Source in Saskatoon. So if you're not familiar with X-ray absorption, the basic idea is that we can change the wavelength or the energy of our X-rays, shine them on our sample, and then we can measure a change in how many of those X-rays, how many of those photons are absorbed by the sample versus transmitted. And so if there is an allowed electronic transition in the material and allowed electronic excitation, then we'll see a peak in the absorption, because that's where those X-rays with those energies are going to be absorbed. And so a kind of characteristic X-ray absorption spectra looks like this one here, where this is an excitation of a 2p electron into a single unoccupied 3D state. So this would be equivalent to copper 2+ with a 3D9 electronic configuration. And this is known as the L edge. So this is the L3 edge and the L2 edge. And this represents the fact that there's 2 peaks here is because there's a spin orbit splitting of the 2p orbitals. So from a measurement like this, we already learn a number of things. So the energy at which these absorption processes occur is exactly specific to a given element. And based on the valence state, which is going to dictate the number of holes in the 3D state, or in the 3D band, we learn about the valence state of the element. And based on the way that those levels are split, we learn about the local environment, whether it's tetrahedral or octahedral. So these are basically all of the questions that we would like to answer about these high entropy spinels. And there's an added bonus, which is that if we perform the exact same measurement with circularly polarized light, a technique that's known as X-ray magnetic circular dichroism, we pick up a degree of sensitivity to the orbital and spin degrees of freedom. And so we can actually calculate the exact spin contribution from every element. And so the way that this works is that the application of a magnetic field to the sample splits the spin up and spin down states by some amount, and you more preferentially have one process versus the other. And so an XMCD signal, a typical one, may look like this if the moment is aligned with the field.
So you measure this after you apply magnetic field, and then you remove magnetic
The
field.
measurement is done with the magnetic field applied. So actually, we just have a, we just have a little neodymium permanent magnet, and it's just near the sample. And so it only works if your sample is magnetically soft.
Right.
Yeah. Okay, so this is the entirety of the data that we collected in our first set of X-ray absorption experiments. You can kind of let your eyes soften because I'm not expecting you to take anything away from this slide other than we have a lot of data. So the way the data here is structured is we have 4 compositions, our 0, 10, 20, and 40% gallium. We have 5 elements, and notice that each of these elements are measured in non-overlapping energy windows. There's no overlap or contamination of the spectra from chromium in manganese. They're very well defined from one another. And then we can look at absorption processes, which is the sum of the left plus right circularly polarized signals, and the dichroism, which is the difference. So a lot of data, very rich data. So to begin to make sense of this data, if you're me, this would mean staring at it for around 6 months. So one of the first things that we can see, if we just look at the dichroism for only the 0% gallium sample, we see that some elements show a predominantly negative dichroism, whereas some elements show a predominantly positive dichroism signal. And this is exactly correlated with our ferrimagnetic order. We have these 2 anti-parallel sublattices. So when I apply a magnetic field, the larger moment sublattice, the octahedral sublattice, is going to align with that field. And the anti-parallel sublattice on the tetrahedral sites is going to anti-align. And so we can see right away, the fact that these signals are not flat, it must mean that each of our elements have a preference for which site they're occupying. So iron in green and cobalt in yellow are preferentially occupying our tetrahedral sites, and the other 3 are preferentially occupying the octahedral sites. Next, we can look at what happens when we begin to throw gallium into the mix. And so the first set of absorption spectra I'll draw your attention to are these nickel scans here, where what you notice as we add gallium in is that the signal to noise gets worse because there's much less nickel by the time we get to the 40% gallium sample. But aside from that signal to noise change, there's no overall difference in the shape of the absorption spectra. So nothing is happening to nickel as gallium goes in. We can exactly sort of describe this 0% gallium spectra as nickel 2+ in an octahedral environment. And as gallium comes in, nickel just stays on that octahedral site. It changes nothing. But manganese is a very different story. When we look at manganese, we see that there are kind of 3 main peaks in this L3 edge. And as we add gallium in, the relative spectral weight of those 3 signals changes dramatically. So to kind of exactly quantify how this changing spectra relates to the changing composition of the material, or to say it differently, to understand how our 5 transition metals are occupying those 2 sublattices, we can perform multiplet calculations where we're approximating the strength of the crystal field that's coming from our oxygen ligands and model these absorption spectra. And so to come back to what Song said earlier about having 10 elements, and I had said there's 11, it's because not only do we have manganese 2+ and 3+, we actually find out that we have manganese 4+, which was an unexpected surprise. And what's remarkable is that in the 0% sample, those 3 manganese states, 2+, 3+, and 4+, are in, they're all in kind of a decent proportion. There's quite a bit of each of them, enough that we can not adequately describe the absorption spectra without accounting for one of them. And there's one more little kind of Easter egg in this data, which is that not only do we need those 3 different manganese oxidation states sitting on tetrahedral and octahedral sites, but we actually need to build in a Jahn-Teller distortion for our manganese 3+ in order to accurately capture the features of the data. So we can learn an incredible amount about what each of the elements is doing in these materials with this absorption method. And so what we see when we go from 0 up to 40, just taking the 2 limiting cases, is that there's an overall redistribution away from 4+ and 3+ towards 2+, which makes sense because we know that gallium has a stable 3+ oxidation state. And so something else has to adjust to let gallium maintain its 3+ oxidation state. So we can take data like that, analysis like that, and we can reconstruct on a site-by-site basis exactly what is the composition of our material So instead of writing the structure like this, where I make no assumptions about those A and B sublattices, I can kind of make this pictorial representation where the pie chart represents what fraction of that site is occupied by each of our 5 elements. And so this is the resulting composition for my 0% gallium material. And now I can actually experimentally calculate what is my true configurational entropy. It was not accurate in the first place to apply this formula to my spinel because we're generally considering a sublattice configurational entropy. And so I have to treat these 2 sublattices distinctly. And so what do we find? We have less than the high entropy threshold. So the entropy of this starting compound is actually in the low regime for our tetrahedral sublattice, and we're in the medium regime for the octahedral sublattice. And whether that actually matters is, I would say, significantly up for debate. And you could also debate whether it's valid to add these 2 configurational entropies together to come up with a combined sublattice entropy. Nonetheless, this is the true sort of configurational entropy of this material. And then we can look at what happens now once we have the gallium coming in. So we can see that we actually don't measure gallium directly, so it's important to point out that gallium is inferred by deduction. But you can see that now on my octahedral site, in this 20% gallium system, I have representation of all 6 elements. So things are actually looking quite promising. And indeed, I pretty quickly move into the high entropy limit in these gallium substituted samples. So, yeah, please.
So, can you remind, so from that formula, there's no configuration, right? Maybe briefly say how to calculate, or easily understand how to calculate this to that.
How to calculate this configurational entropy?
Yeah, because that doesn't have any like tetrahedron information or octahedral information.
Right. So for say the 0% sample, I'm treating this one separately first and then doing this one. So that's what the 2 bars represent. And here I have roughly, say, 0.6 is cobalt. So then my first species is 0.6 ln 0.6. And then I have maybe 10% of manganese. And so that's 0.1 ln of 0.1. So you add up all the contributions. So it does assume nothing about the geometry. Yeah, the geometry is not important.
Thank you.
Yeah. How am I doing on time?
I think
Poorly.
we have had questions. I mean, I guess it goes on till 45.
Okay, so I have a bit of time. Okay, great.
Good question?
Yeah.
Okay, so you don't have nickel 3+, so that's still
No,
10.
we don't have any nickel 3+.
Oh, you do?
No nickel 3+.
So it's still 10.
It's still 10.
Maybe 4+. No, I'm joking. That's
Yeah.
a joke. The real question is this. Your question is, so I don't know if you were aware of this, but there is something called octahedral stabilization energy.
Mm.
Have you thought about this? This is a well-established concept.
Like the crystal field stabilization effects.
Yeah, exactly. The numbers are known.
Yeah, exactly. Yeah.
Numbers are known. Yeah.
Yes.
So okay. So I think you can check kind of consistency with
Yes.
your results.
So yes, we have done this actually. George Swansky encouraged us
George
to do
should know this.
Yes.
Yeah.
So it's mostly consistent. In fact, a priori, before we had done the X-ray absorption experiment, George wrote down what he thought was going to be the composition of the.
Exactly.
He was mostly right, but he had, now I can't remember off the top of my head. I think maybe he had something wrong about the manganese and the iron because he hadn't contemplated iron.
Roughly is correct. Yeah.
Roughly correct. Yeah. It's mostly in agreement, yeah. So one thing that we haven't done yet, but that we need to do, is to look then, since we know what are the oxidation states and the proportions of the different elements, we actually should be able to calculate the ordered moment from that. And from that, we can learn, is the whole material 100% magnetically ordered, or are there non-magnetically ordered domains? It's something we have no, because both neutrons and magnetization are only giving us the average, so we can't say. Okay. I have 2 more parts to my talk, but they are quite brief, so I'll try to go quickly.
Sorry, could it be done like muons, I guess?
So there's a couple challenges to doing muons. The main one is that the onset of order is at 400 Kelvin, and at those temperatures, muons diffuse. So I don't know that we would learn that much about the magnetism distinct from the muon diffusion.
But why do you have to be at high temperature?
I mean,
Oh, because you mean if you just wanted to measure the magnetically ordered volume fraction? Okay, so my assumption is that if we have non-magnetically ordered regions, they would be on a kind of nano domain scale, and the muon would still feel the magnetism from at that length scale. So I'm not imagining that we have a micron length scale non-ordered regions. Yeah, that's my feeling, but it's probably worth to do.
But if the muon has some preferred site, let's assume it's one preferred site,
Mm-hmm.
then wouldn't it sample sort of five different environments? So you would see.
It's sampling infinitely many environments because
No, but I mean, like, there's sort of 5 different local transition metal environments.
muons tend to sit at interstitial positions. So at any interstitial position, it's going to have nearest, several nearest tetrahedra and several nearest octahedra. And those are going to be, there's going to be like thousands of different possible configurations for those.
Oh, I see, because it's 5. Okay.
Yeah. Okay, so my, as I had mentioned before, my background is in kind of quantum magnetism, and actually we got a taste of this in JP's talk, which is that kind of common plight in any sort of quantum state of matter is how disorder is going to affect that kind of fragile state. And well, this is very different than that, obviously. We're deliberately introducing disorder, but the question is, how perfect is that disorder? And my intuition for this was that just as it is impossible to make a perfectly ordered material, it should be equally impossible to make a perfectly disordered material. And synthetic conditions should matter greatly. So what we set out to do is to grow a single high entropy material with nominally identical composition, nominally the exact same chemical formula, by 5 different synthetic methods, all in bulk, that would sample different thermodynamic and kinetic reaction conditions. So they're sorted on this kind of rough axis. It's not completely perfect, but generally going from left to right, we're improving reaction kinetics, and generally going right to left, we're accessing more thermodynamic control. So we're more likely to be accessing the thermodynamic ground state. And so one thing to point out is that these methods kind of occur in different media. And so solid state is a solid-to-solid reaction, whereas in combustion, we're dissolving all of our reagents into a solution and making a gel. And so these are very different when we think about the process of what's going on. So the material that we're going to continue to work on is the spinel, the exact same 0% gallium structure that I showed you previously. And a very attractive aspect of spinels is that they really are amenable to be grown by a number of different methods. Okay. Oh yeah, I tried to use animation. When we produce these materials, the first thing that we see is that at the average level, they are equivalent to one another. So if we do X-ray diffraction, X-ray powder diffraction on our 5 different samples, we see that there is kind of negligible variance in their lattice parameters, in their adjustable structural positions. These samples look really equivalent. There's minor differences in sort of peak widths and those sort of things, but no more than you would see in just 2 samples prepared to kind of batch-to-batch variance. And a second thing that we find is that when we look at this same X-ray absorption, so the label up here says manganese L3. So recall that manganese was that very susceptible ion, that when we added gallium in, it was the one that did the changing. So it's the one that we think should be most likely to adjust if things are really changing from one sample to the next. And what you can see here is that the shape of this absorption spectra is really not changing from one sample to the next. We have those same 3 peaks in all 5 samples, and they're in very similar ratios to one another. So at the average and at this kind of local scale, we think that these samples look very similar to one another. But where things get quite interesting is if we look at intermediate length scales. And so next I'm going to show you data for just 2 of our samples produced by molten salts and combustion, where we're going to look at the micron scale. So this is an SEM micrograph for our 2 samples. So for the molten salt sample, what we see is that the material is forming these very nice micron scale crystals. We can even see kind of typical octahedral facets at that scale, whereas the combustion sample is this highly networked and porous solid, and it doesn't have well-defined sort of grains. So the grains are sort of spherical. Now, I want to introduce a technique which is called micro-XRF, so micro X-ray fluorescence spectroscopy. This is a measurement that we performed at the ESRF. And what we're doing in a micro-XRF experiment is we're measuring the fluorescence signal from our sample, again with micron scale resolution. And we're performing a quantitative measurement, so we can look at whether the fluorescence signal across the sample is in proportion for each of our 3 elements. And so the legend to understanding what you see here is shown in this triangle inset, where we can only plot 3 elements at once, but it's kind of representative of what's going on. And so if you see a pixel that is blue, red, or green, it means there's an excess in the fluorescence signal of one of those elements. And so what we see with our molten salt sample is that it's pretty green everywhere. So there's an excess of iron. And then we see that there are these small regions in blue and red where there's an excess of either manganese or cobalt, and a region here that's kind of yellow, meaning that it's manganese deficient. And so that molten salt sample on a micron length scale, each pixel here is about 4 microns, is massively inhomogeneous. It's extremely chemically inhomogeneous. And I just want to clarify that compared to that atom probe measurement I showed you on my first slide, where we had all those pixels as the atoms were evaporating, a method like that is not quantitative in the same regard. So this sample would still look homogeneous if we did this atom probe tomography. It's not that these elements are missing in any region, it's just that they're in non-equal stoichiometries. Now, if we look at the combustion sample, what we see is actually something that looks like an SEM image because it's entirely gray and white, and that's because our 3 elements represented here are in roughly equal proportions everywhere. So this sample is extremely homogeneous. So then the question that we were interested to know is, what do these kind of microstructural differences have on the magnetism? We would expect that being iron-rich and inhomogeneous and having very different grain morphologies, these in general are things that will lead to differences in bulk properties. And what we have been kind of astonished to find is not just across these 2 samples, but across all 5 samples produced by very different synthetic methods, the magnetism is very resilient. So while there are differences in the shapes of these magnetization curves, the overall behavior is incredibly consistent. We have TCs that vary across the series by less than 5%. The saturated moments vary by like 2%. And these 2 samples happen to have identical coercive fields. So we would say that in spite of these sort of microstructural differences, the magnetism in these materials appears to be quite resilient, which I think is very surprising for a material as complex as this. Okay, last and finishing with a bang. And this, I was really disappointed to have missed this panel discussion yesterday on applications of machine learning to different problems in quantum materials. And I think this will fit in nicely with that theme. So we've been thinking about how to apply machine learning to optimizing HEO properties and also to understanding their stability regions. We're in a very compositionally complex space, and so knowing where materials might exist is very challenging. So in order to accomplish this, we have collaborated with Stefan Bauer, who's at the Technical University of Munich. And he is a machine learning specialist. And so we wanted to identify initially sort of a problem that had a reasonable scope. And so the problem that we've settled on identifying is one in which we will prepare a training data set of hundreds of different spinel high entropy oxides with varying stoichiometries. So I focused today on that equal stoichiometry, 20, 20, 20, 20. But of course, you can vary from that in any number of ways. And you can do so in arbitrarily small increments. And it's incredibly unclear at this point how those small incremental changes might influence things like magnetic ordering transition temperature, the coercive field, and the saturated moment, all of which are technologically useful properties, especially for a class of materials that order above room temperature. So I have these 2 very talented undergraduates who over the last 8 months have prepared hundreds of spinel high entropy oxides of different composition. And for us, we're not a high throughput synthesis group, so this is not in our natural wheelhouse. And so preparing samples, that many samples, it's not straightforwardly obvious to us how to do that because our normal synthesis work is very slow. We're not producing hundreds of samples even in a year, usually. And so to speed things up considerably, we've devised this combustion method, and I'm going to show you one of our early combustion attempts where we were still working out some of the kinks. So keep in mind, it's called combustion.
One of those YouTube.
Yeah. So now we know how to do this without making a massive mess and spilling our product all over the hot plate. But what is amazing is that is entirely real-time video. It's not sped up in any way. And that chemical reaction is taking place in seconds. So, there's some work that goes into the preparing of the solution, but the synthesis itself takes place in seconds. And once we just put that sample, that product in the oven for an hour, it comes out as beautifully crystalline, very clean X-ray diffraction patterns. And so we've been able to survey hundreds of compositions at this stage, which I hope to come back to a future ICANN meeting and tell you about the results of our machine learning efforts. So I will conclude there. There's one person who's been involved in all of the work that I've shown you today, who's Mario Gonzalez-Ribas, a very talented PhD student. And I would just like to close by emphasizing that in this topic of high entropy materials, I think at this stage it's fair to say that there are still many more open questions than answers. And so I think it's a field with a lot still to offer. And thank you so much for your attention.
Maybe we can have just one question.
So when you're using atom probe tomography, you only got the 1 angstrom resolution vertically. You don't have it laterally. So what do you worry about that?
I don't worry about it at all because I don't do atom probe tomography. Actually, that's the data for another group.
Okay.
Yeah.
But you don't have it in all 3 dimensions, that's the point.
That's right, yeah, so you're yeah, that's right. I wouldn't assume so. I think that given that the material that's being studied in atom probe tomography there is cubic and it's polycrystalline, there's no reason that there should be any shape anisotropy within the tip. So if you're measuring in one direction, it should be representative.
Okay, maybe one last question.
So just short. So when you compute this entropy, you didn't count this different balance, right?
We did actually.
You did?
Yeah.
Oh, still it's a low entropy.
Yeah.
Oh, that's interesting.
Yeah.
So now
So actually, only manganese exists in multiple oxidation states.
others are only one balance.
Manganese is only in one valence, and everything else is only in. Or sorry, manganese is in 3 valences. Everything else is only in 1.
One balance. Oh,
Nickel
that's
is 2 plus, chromium is 3 plus.
That's interesting. So you use a different synthesis technique, but still all of them were done more or less in air.
Yes.
In air. So because of this balance, it can be sensitive on oxygen partial pressure. So if you change oxygen partial pressure, very much, then this balance may change. Then this entropy and all these things could change.
That's right. So one thing we know, we've done quite careful thermogravimetric analysis. They actually do differ quite a bit in their oxygen concentrations.
Oh, actually they do.
They
but
do.
Still entropy.
So still the preference is overall, yeah.
I see. Okay, interesting.
Yeah.
Well, let's thank all our speakers again and to visit the posters, and also there should be some refreshments here.
Thank you so much. I thought the room was
That's good.
really
No,
exciting, but now that I've been standing up
it's a longer lifetime.
an hour. We didn't know much about that. The gallium stuff that turns out that it's gallium. Something else. So, what do you mean, what's the composition we know? Yeah, so especially in the case of solid state metals, we know exactly like what happened is what must happen. Well, if you monitor mass loss, let's say. Yeah. Thank you. I don't know.
I know the, yeah, I hear it on the TV, but.
Yeah,
just clarify.
That's where I grew up. So,
I'm from the area.
Okay.
yeah, I'm really
Graduate from university.
Really, I didn't know.
Yeah, I think coal, there are two, and the other is the brewer.